no significant training time involved, but you still want to take some time to get started on it. Okay.
No significant training time? Does it take like 4 hours?
Yeah, but I don't think you actually have to produce a result as part of the lab spec.
Okay.
You just have to modify the code. I mean, so it should run. You should be able to run it on the general conference training data set. But nowhere does it actually say, like, finish training. Just saying. Maybe I shouldn't have pointed that out. I think you have to like show some results of your training, but they don't have to be good. I mean, there's no measure of goodness.
Wait, so for this, like, so we should just take the IPython notebook like as it is, and then just change parts of the code to make it work within our focus data?
Yes.
Okay.
Yes, that's it. So okay, so he said, sorry, oh yeah, deepfakes. I was looking at some Star Wars Solo. Yeah, this is the Han Solo deepfake. It's really pretty good. If you have time, there's Han Solo's face instead of Alden. I don't know, say it. No, we're not going to watch this right now. We're not going to get distracted. Okay, so if you go to, you should all get distracted after class. So you go to the lab spec. Okay, so the question was, wait, so all we have to do is get the annotated notebook running on the general conference data set? Yes, that is it. So you do 50% of this lab is just you reading and understanding it. But the only way that we evaluate that is if you actually are able to load and train on the general conference data set. That's all you have to do. The point of this lab was A, to be easy, but B, to, like I said, give you experience with a different style of assignment. Understanding other people's code is very important. And so if you do want the extra credit though, then you actually have to like finish training and do some comparisons. Okay, good. And hopefully you all found the annotated transformer code, so we'll go through this, like I said, a little bit later. Any other questions before we dive in? Yeah, go ahead.
Has anyone had any problems just running it as is? Because I would like run it and probably down and run some.
Yes.
Yeah, it's on Piazza.
Yeah, I think there's been some chatter about that. So I think the Piazza answers, I think, are solve that. Is that?
Yes.
Yep.
Yeah. Okay. Yeah.
It doesn't solve all the way. So when you use the answer in Piazza, the graph that you get is completely different from what it should be.
The graph. Which graph?
The sine graph and the cosine graph.
Oh, the positional encoding graph. Oh, interesting. How does it look?
Completely different.
Like stylistically different, or like informationally different?
Like not a sine wave.
Really?
Yeah.
Style transfer.
Like a Van Gogh. Oh, what does it look like? It's just.
Like a sawtooth thing. I don't know.
Oh, interesting. Okay, is that important?
I don't know.
She is. We look at that.
I just find that to be important. I could still train the whole thing and translate it.
So, if you, the changes that are made that make the graph look different is because you're using the latest version of PyTorch. So making those changes to convert them to floats and then longs and things like that, that's what changes the graphs. If you run on an old version of PyTorch, like 0.3 something, which the notebook has commented out as an install, then it will graph that properly. I mean, like, because all the code was written on an old version of PyTorch, it's no longer valid, or it's not the most recent version anymore. So in order to run the notebook, you actually have to install the old version of PyTorch,
which is super easy.
unless you want to make changes. However, even that, I still couldn't get it to run all the way. There was a couple more things that just seemed like it was still having troubles. When it actually came time to training, I'm still in the middle of trying to figure out some other things that are causing problems even with the old version of PyTorch. So you have to install an older version of PyTorch and a particular version of Torch text for sure in order to get it to work. And then I'm not sure about the other things I'm still running into.
Okay.
Yeah, that's just a function of PyTorch doesn't support backwards compatibility yet before version 1.0. So that's just a pain in the ass.
Yeah.
Okay. I'm sorry about that. I didn't realize it was that complicated. So for future posterity, we will try to streamline that a little more. But it sounds like this is well understood on Piazza. We know how to mostly get it working.
Has anyone got the notebook working all the way to the end, including training and all that?
Besides you? Okay, a couple
What else did
people
you
have.
have to do besides?
Couple people-
using
what else did you have to do?
I just did those two things. So I used the install, like the pip install from the Alexander's notebook, and
Yes.
then I just used that Piazza to install the torch text version. That worked.
Okay, good. What did you have to do? Same
Same
thing.
things, torch, 0.3.0, and then torch text 0.2.3.
Okay, so if you do just those two installs, then everything else works, okay? Okay, so that sounds like the simplest way, maybe to get things working appropriately. Yeah,
I just want to double check, it sounds like this is the case, but all this has been documented.
document of Gaza, is that true?
Let's
So-
find out.
Could you please send me a note with whatever it is exactly it is that you installed, and I'll put that in the lab spec, and we'll also post it to Piazza just so that everybody can just cut paste and get going.
I remember what the problem was. I could run the notebook, but the notebook by default doesn't actually do any training. It loads a pre-trained model. Are we supposed to train? Because the notebook is like doing a multi-GPU setup with like 4 GPUs and splitting things across. So there's a lot of code modifications required to get it to work on a single GPU, I think.
So the Colab
Um,
version has a single GPU example.
Oh,
One of the
I've
versions
not
has a
seen the
single.
collab version. Okay, I'll look at that.
Oh, that's an important difference too.
Yes. So it's a different notebook then.
Yeah,
Okay.
they are different notebooks.
Okay, that's
And the
good.
Colab version, that's probably what the problem is.
So don't use this notebook.
Okay, yeah.
Yeah.
Sorry if that wasn't clear, yes.
Does that link on the bottom?
There's
It
this
does
link
say
right
wow.
here. There's this collab version of the notebook.
Sorry.
Oh, thank you. That's gonna save us so much time.
It was just, I put one sentence in the spec, I definitely should have made that clearer, sorry.
Okay, apologies about that. So yes, use that. Okay. Good. Any other questions? Yeah.
I wanted to ask what you meant by cleaning the data. What needs to be cleaned exactly?
So this is flexible. I mean, just like get rid of maybe crazy punctuation or like get rid of quote marks maybe. Andrew, what did you do, Andrew?
Yeah, so another example, in the CSV, you have to be careful for empty rows, that kind of thing. If you try to train on a row that's empty, it may not work because of the way it's split. I don't know, just don't, I guess the purpose of that is don't assume that it's perfect for your model. Do a little bit of, it might be, but it might not.
I'm training right now. And
Okay,
It sounds
if it's
like
working-
I did different things because I didn't use this notebook. I like went and got code from it and made my own notebook and
Okay.
set it up kind of different. And I know I'm using it and it like tokenizes everything for me using
Oh.
that stuff. And it's running. But
Awesome.
I have no idea what it's going to
Then-
come
then
out
that's
at the
fine.
other end.
Yeah, that's great. But we don't want this to be hard. So when in doubt, do whatever's simpler. Okay? And if that means not thinking that much, as long as the code doesn't explode, then that's fine.
So if it trains, but we didn't have to do any cleaning on it?
That's fine. That's,
Okay.
that's great. When in doubt, go simple. Okay, good. Good. Okay, then let's talk about the transformer a little more in detail. So last time we we talked a little bit about conversational AI and these neural conversation models, as well as a little bit about word embeddings, and we just about started on the transformer. But today, oh man, these are the wrong images. Ignore those. Today we'll talk about transformer, and we may even get to this BERT paper. It's super annoying. So I was like, oh, super excited to tell you about the transformer because that was like the latest, greatest paper. It came out like a year ago, but then like just yesterday, Google released another one that's now the latest and greatest. And I was like, shoot, I can never keep up. Okay, so just to remind ourselves, before yesterday, this model was the state of the art. And it's doing great, like we're getting really good BLEU scores across a number of different training tasks. And the big ideas are, we're rethinking time. And so we have this sequence of data which you might think you need to read left to right, but the history of neural machine translation has said, you know what, actually there's no reason to limit ourselves to reading left to right. We can read left to right, we can read right to left, and we can read in parallel. And that's kind of the big idea behind the transformer, is we're going to take a sequence of words. We've got a sequence of embeddings representing a semantic meaning of those words. And we're going to go through a systematic number of transformations to calculate new representations of all the words, and we'll use those to decode the target sentence. Okay, and I think I showed this little video, so we're going to try to make this video very explicit today as we go through it. So kind of the idea is that we have a representation of all the words, and then at each layer of processing, we calculate new representations of the words, where the new representations can depend essentially on anything in the past. Then when we decode, we calculate output words as a function of whatever was encoded as well as previous decoding steps. Okay, and so I wanted to kind of take you through a little bit of the examples that they showed in the blog post, because I was very interested in some of these examples. So here's an example where they were talking about some of the properties that this model has. Because this model goes through and calculates, so sort of attention all the way down. That's why the paper is called Attention is All You Need. There's no recurrent neural nets. Everything is attention or self-attention. And so what you can do is you can go through the model and you can ask at any point, what words did you think were most important in calculating a new word? So here's an example of why this kind of analysis is cool, because we can, well, here, sorry, I'll show you. So here's a traditional problem in neural machine translation. It's called co-reference resolution. So consider the top sentence. The animal didn't cross the street because it was too tired. So what does it refer to? The animal. How did you know that? Because streets don't get tired. Okay. You might hear neurons told you. Okay. The animal didn't cross the street because it was too tired. So we think that it refers to the animal because streets don't get tired. Okay. But consider this sentence. The animal didn't cross the road because it was too wide. What does it refer to? The animal. Right, get out. Probably the street. Thank you, Will. That was the right answer. Good point. Okay, so in this case, it refers to the animal. In this case, we think it refers to the street. Now notice that if you were reading the sentence left to right, you wouldn't know that until after you had seen this word. Okay, so here's the problem. The problem is that if you translate this sentence into French, if it refers to animal, animal is a masculine pronoun. And so you need to output the masculine version of it. But if it returns to street, that's feminine. That's a feminine noun, and so you need to output the feminine version of it. So you need to know which thing this, so you can't just spit out some generic it word translation. You have to actually know what it's referring to get the gender pronoun correct. Okay, and so this poses a challenge. Apparently, if you type this sentence into Google Translate right now, it'll do the wrong thing. Like it can't handle this. But the transformer can't. And so here's what it kind of looks like. What it looks like is, as you're constructing these successive representations of words, and you look at the attention, and this is, I think, like the second to last layer or something, you see that this word, when we calculated a new representation for it, when we said it was too tired, this word depended on all of these words. So the links represent what it was attending to, and the color, the darkness of the link, represents the strength. So in this case, this representation was calculated as a function of all of these, but it most strongly depended on animal. Whereas in this case, it most strongly depended on street. Okay, so that, like, you can just analyze who was attending to what, and you can see how it is that the neural net came up with its answer, which I think is pretty cool. Okay, so how do we learn to do this? How do we set up the architecture? What does it look like? So the paper shows you this, right? Which I was like, okay, let's see if we can go through this, and let's see if we can figure it out. So this is like the sort of the big picture architecture, and it's roughly an encoder-decoder architecture. This is the sort of thing we've talked about. It's just that the encoder and the decoder have a very particular kind of form. So you have inputs here, and they go through an initial embedding. So this is words. This is your initial embedding. This is this positional encoding thing, which we'll talk about just a little bit. Then there's a stack of these encoders, n of them, where n, I believe, is 6. So you get 6 of these things. And there's a couple of features that you can tell just from looking at this level of diagram. So what do you notice? What are some architectural features that you notice? Yeah. Skip connections. So right here, this line skips that, and then you have some add. And then there's a norm. Basically, this line is skipping this multi-headed. Okay, good. What else do you notice?
Every time this block on the right is repeated, we have a link going to each of those blocks from our encoded block.
Yes, you mean this link right here? Yep. Okay, good. What else do you notice? By the way, I'll point out, there's like skip connections everywhere, right? So there's skip connections here, there's skip connections here, there's skip connections here. Okay, so skip connections are like, they're like the default. It's like you don't do anything without skip connection. Go ahead.
The decoder still has some form of like self-feeding loop, kind of like a recurrence relation, but like the outputs become just secondary inputs.
So you mean the outputs of this
Um,
become the inputs of the next layer? Or,
yeah.
yep, okay, good. Yeah, so it's almost like a recurrent thing, but that we're unfolding it in time a little bit. Yeah, so by stack, you're right. Now I think that's not exactly true though. My understanding is that the parameters of this block are not tied as they're stacked. So it's actually, you're actually able to learn a different decoding function at each level of unstacking. However, the architecture is preserved. It's not exactly like recurrent. Yeah, Scott.
So, this may be just me not understanding the page. How do we know that the skip connections are actually, for example, skipping the multi-headed mention, and then we're not feeding the input there, and then kind of doing like what we did with recurrent, where now we're gonna treat that input as like a hidden layer and feed that into the next.
Oh, I see. So you're saying, hey, this looks like the same figure as a recurrent neural net.
Right.
Yeah, good question. And I think the answer is you would probably have to look at the text.
Okay.
Or just note that there's no notion of time here. Usually if there's a recurrent, you'll see like t and t plus 1 and t minus 1. That's not here. Okay.
So to generate this, I guess the output sentence, the translation, you have to run through this block on the right, like until you hit. So you run through it once, you get one output, then you shove that back in and run through it again until you get an end character.
Yes, I believe so. So decoding, so encoding is done in parallel. All of the inputs, you stretch them all out, and everybody calculates in parallel, which is one of the virtues of this architecture. But decoding is done sequentially, and that's kind of has to be that way. I actually think it would be quite interesting as a research project to ask if there's other ways to generate sentences. So for example, you could imagine a hierarchical generation, where we generate a tree, or something like that. So it's like, oh, I need to generate a sentence. Okay, I'm going to generate the noun phrase, and then I'm going to generate the verb phrase. And okay, to generate the noun phrase, I need the subject, and to generate the verb phrase, I need the object, and then the adverb, you know. So generate it that way, in a non-sequential way. I don't think anybody's ever done that, but you could.
So what it means by like output shifted right is it's saying you do the input until you've done everything parallel, then you get the first output, and then you plug that back into the right part, and then you take the next
Yeah.
plug back in.
I
So
believe
the
so.
first thing is just parallel, and you repeatedly do the same part.
Yeah.
Okay.
Yeah. Okay, good. Other observations or questions? Okay, and I think we understand. Oh yeah, go ahead.
Just to clarify, the attention thing that's happening is what we looked at in the last slide where it says,
Yes.
I think it's connected to these 4 words.
Yes.
Okay.
So the attention thing is a little more complicated here, but it's the same basic idea. We have, so in fact, we'll talk about this kind of on the next slide. So yeah, just hold that thought. We'll get to it. Any other observations? Yeah, so I think this is, I think one of the virtues of this architecture is that it's actually rather simple. I mean, when we look at it, maybe the figure looks complicated, but it's composed of pieces that we all know and love. So the attention mechanism we'll see is quite simple. Skip connections we know how to do. Adding in norms, no problem. Feed-forward network, no problem. The positional encodings are a little bit interesting. So the positional encodings are necessary because if the network wants to take advantage of the specific position of a word, it doesn't know how to do that because we've parallelized everything. And so what we do is we give the network an additional representation of where the word was in the sentence, and it can then learn to extract features from that if it feels like it's useful. The specific representation they use is this crazy, this sine wave thing, where depending on your position in the sentence, it's essentially this combination of sines and cosines, which I thought was interesting. So this is almost like a Fourier decomposition of a one-hot coding of the position, which, cool, like, okay. Okay, so let's talk about attention a little bit. So attention, as implemented here, they called it a scaled dot product, like attention. And the idea is very simple. So and this is a very abstract look at attention. So as you consider this, I want you to think about maybe not neural machine translation specifically, if that's not your field of interest, but rather think about times when you may need to learn to attend to something, and just think abstractly about this architecture. Okay, so the way that it's written about in the paper, they say you have a series, you have three things. You have queries, keys, and values. And those are all distinct. And so the way I imagine this, I'll just draw a little figure here, is, so think of a dictionary. We have keys and values. And they can be different types of objects. So keys, for our purpose, are just vectors. And so you might have a set of keys. Think of them as a set of k-dimensional vectors. And k key. And then you have values. And values are some other size thing. And those maybe are v-dimensional vectors. And so what they're saying is they're saying, let's take our query. So we're going to take a query vector, and we're going to compare it to each key. And that's going to give us some measure of similarity. And so if we find the key that we want, then we'll return the value that we can, the corresponding value. So how are we going to measure similarity? Dot product. Okay, so and that's what this little graph is representing, but I actually find the equation a little bit clearer. So they think of their attention mechanisms as consisting of a set of queries. So this is a set of query vectors, and then a set of keys and a set of corresponding values. So let's see if we can unpack what this is doing. This is the entirety of their attention mechanism. Yeah, Brian.
So the Q times K transpose is the dot product between the query.
Okay, so so how's that working? You're saying that's the dot product. What do you mean?
Well, we're transposing the key vectors. So with these two vectors, right? Queries, so it's a bunch of query vectors stacked on top of each other, with the key vectors all stacked up each other, so the two matrices. And by transposing the key, the matrix, we're transposing all of its vectors so that when we do the matrix multiply, each of the individual query and key vectors are dot product.
Okay, so I think you're saying this. You're saying we start with a matrix of queries, a matrix of queries and a matrix of keys, and these are potentially different sizes. And so if we want to calculate the dot product of everything in this matrix with everything in this matrix, we can do it in one matrix multiply. And that's, so we take this, and now, remember we talked about this like in lecture number 2, how do you interpret matrix-matrix multiplication? We can think of it as a series of dot products. So we take this and this, dot product them, this and this, dot product, calculate every key with every query. And that gives us what? A matrix of similarities. Yeah, so let's say we have little q queries and little k keys. How big is our matrix of similarities going to be? So this is little q rows, this is little k columns. Matrix of similarities will be what? Q by k? Okay, good. So that's this term. So we're querying all of these things. Now we take the softmax of that. So what happens now? What are all these numbers? There's scores between 0 and 1. Do they sum to 1? Do they sum to 1? According to this.
I'm going to say no, because otherwise we would have bought the softmax.
We're normalizing it.
Yeah, there's no normalization here. There's no sum. As far as I know, as far as I can tell, they are numbers between 0 and 1, so they're weights, but they do not sum to 1. So, sorry? Not necessarily. You mean normalized being unit norm vectors?
Yeah.
No, not necessarily.
May not even be minus 1 and 1.
True, yeah, your similarities could be a little bit wild. Yeah. Okay, so these are, as far as I can tell, are not summing to 1 in any dimension. But they're still weights. Okay, then we multiply by the V matrix. So what's going on there? Yeah, it's a weighted combination. So we have some V matrix. And how many rows will the V matrix have? K, right? Because it has the same number of rows as the queries. And so we'll take one of these rows, which represents the similarity of a query with every key. And then we'll take this vector of weights and multiply it by V's. And it will sum them together according to the weights. And that will give us a weighted value. And we'll do that a few times. Yes?
Just for quick clarification, what is the DCK? Is that the dimension of K?
Yes. And the reason for that is explained in the paper, but they talk about how if you take a bunch of random things from a Gaussian and you dot product them together, the mean will be 0, but the variance increases as the dimension of the vectors increases. And so that's a scaling factor to just keep everything about the same, about unit variance. Okay, so that's it. So this little equation is their attention mechanism. Pretty simple. Yeah?
So just for clarification for me, our queries, is that the sentence we're inputting in? We're trying to, our query, is that the sentence that says the dog ran across the street, we want to translate to this French? Is that what our queries are?
Yeah, so good. So they talk about this in the paper a little bit. I think it's clear in the notebook. But everything, so there are many different times that this attention mechanism is used in this model. So it's used on the encoder side as we go from layer to layer. There's the self-attention, but it's also used on the decoder side. The decoder has some attention, that's self-attention on the decoding side, but it also has some attention onto the encoder side. So it's used in a couple different places. Does that help?
Yes.
And the other thing that they said, which I thought was a little unclear in the paper, was that both the queries, the keys, and the values all come from different parts of the model.
Because I understand the mathematical properties of
Yeah.
the similarities between the key queries, keys, and values. Just what exactly those are in the bigger contexts.
Yeah. I think when we go through the notebook, hopefully that will become a little clearer. Any other questions? Okay. So here's the positional encodings. The last thing that I thought I wanted to point out to you that I thought was super interesting was this. Learning rate schedule. So we've talked about learning rates in this class. You take your atom optimizer, and there's some number you have to put in, which is the learning rate. And we've always used some fixed learning rate, 0.001, something like that. In this paper, and in a lot of papers kind of in this area, they use a variable learning rate. And not only is the learning rate variable, it changes in very strange ways. So I just wanted to talk about this particular learning rate schedule. So this is steps of optimization along the x-axis, and this is the learning rate along the y-axis. What is going on and why are they doing this? So it starts off low, goes high, and then decays. Why?
Looks like they want to let the weights kind of figure out something close to what they should be before they start really moving stuff towards that.
Okay. Sort of let it figure itself out a little bit. Go ahead.
Is it with something to do with the skip connection? So they're trying to let things kind of settle in the parts that are just getting skipped, and then it kind of tails off again, so the more complicated stuff can kind of sort itself out.
Could, yeah, complicated stuff, sorting itself out, maybe letting information flow, something.
Just in my mind, I'm thinking you're going through this big space, right? And you have a higher learning rate to kind of make bigger jumps into the space. and then eventually, hopefully, you kind of settle into a valley somewhere. But then you want to try to get into, you want to take smaller steps so that you get closer to a minimum rather than jumping between hills
Okay.
and a valley.
Okay, so I think we all agree that the intuition for the decay part is exactly what you're saying. Like, yes, bigger steps at the beginning, smaller steps when we get sort of closer and we're trying to whittle things down. Adam is supposed to adaptively do this, but hey, there's no reason why we can't also force it to do this. I think that's a good explanation of why we want to start high and decay low. But why do we start low and then bump high first? Yeah.
Is it because our gradients are already huge at the start where we're like way off the mark, so there's like very clear gradients, and so we don't need a big one?
I think that is the answer, yes. So the proposal on the table is it because at the very beginning your gradients are huge? So the answer is yes, for a couple of reasons. At the very beginning, you're wildly inaccurate. Your model is way wrong, and so all of your errors are going to be very big. As that propagates through, that's going to give you very big gradients. And so if you take a big step or take a step with a big learning rate and your gradients are really big, that's going to knock you into some crazy part of the parameter space. And might, for example, undo all of the careful initialization that you did with all of your weights. And so at the very beginning, your gradients aren't that reliable. And so you actually don't want to take very big steps because it'll knock you crazy places. So you take small steps until you get a little bit, and maybe you probably have all seen this. In every DNN training curve that you ever see, the first couple of steps, you make tremendous progress. Things are changing a lot. And then things kind of settle down and you start decaying sort of at a more reasonable rate. But so empirically, they've found that you just want to really be careful about those first couple of steps of your optimization. So start low, bump high. So here, we're hoping that the gradients are going to be good and clean. And we want to take big steps, but then eventually decay. So I think this is a generic insight from many networks. And you should probably think about this when you train your networks. Okay, so let's flip over to the notebook. If you haven't looked at this notebook yet, I strongly encourage it. You're welcome to follow along. And we're just going to try to go through this, and I'm going to point out some things that I think are particularly nice about this. So thanks to our TA Andrew for finding this. I think it's a fantastic resource. It is a great, I think this is just a beautiful piece of pedagogy because what they've done is they've taken this paper and they've implemented it, and they've just taken things straight out of the paper and then shown you how they implemented it in PyTorch. What I think also is nice about this particular notebook is that I really liked their coding style. I felt like they did a really good job of using PyTorch, and so I hope that you'll learn something about good PyTorch coding style as you go through this. Okay, so let's just dive in. Preliminaries, import a bunch of stuff. Blah, blah, blah. Okay, so the first thing they do is define an encoder-decoder class. And what you'll see here in the next couple of cells is you'll see multiple classes that are all refining an idea and getting more and more specific. So the very first class is just the general idea of an encoder-decoder architecture. So it's an encoder-decoder, it inherits from module, and it's very, very simple. So this is a super high-level module, but it says, you give me something called an encoder, something called a decoder, something called a source embedder, and a target embedder, and this thing called a generator. I'll remember all those things. Okay, so then when it's time to do the forward pass of this encoder-decoder thing, what do I do? Well, I encode, and then take whatever the result of that is, and hand it to the decode. And what does encode mean? Well, encode means I call that thing that you gave me, whatever that encoder thing is, and I encode the embedded version of whatever the source thing is, so whatever your data is. And maybe there's this mask. And then what does it mean to decode? Well, I take whatever the target was, I embed it, and then I decode it. And then maybe there's some memory and some masks. And that's it. So you might look at this and you might think, well, this class almost feels like vacuous, right? Like there's no details here. And that's right, there's no details here. And that is, I think, the beauty of it. It's just an abstract encoder decoder. You still have to provide all the details. Cool. Okay, any questions about this? Yeah.
This might be a dumb question, but I've wondered this for a while now. So like when you had that call, like the self.encoder, it almost seems like you're treating that class instance like a function. How does that work?
No, they're passing it
Ah.
at the very top.
Well,
Yeah.
I know, but like that's like an instance of a class, right?
So encoder, right? Okay, so welcome to Python. Encoder can be anything that is callable. So it could be an object that you can call, or it could be a function, like an anonymous function. And we're just going to, or not anonymous function, I guess. And we're just going to remember that function.
Right.
So you hand me a function called encoder, and then I'll call it later.
But like, so later on they instantiate like an encoder class, and that's what they pass in. But it's like they're treating the class as a function.
So when you call self.encode, it calls the forward function of the encode class.
Which calls the
So like how does
underscore underscore call underscore underscore method.
Oh, so
Yeah.
there's like some hidden
Make
method
an
that's being
object,
called?
Yeah, so there's
Okay.
in Python, yes, in Python, objects have this underscore call thing. And it's like, if you call the object as if it was a function, what happens?
Yeah.
And,
Okay.
and
So
here.
that's all happening like somewhere under the
A little bit under the
hood.
So, well, that's a general Python thing, but I believe that's because nn.modules forward. Yeah, so like anything that inherits from nn.module will have the property that if you call it as a function, it will actually call forward.
Oh, interesting. Okay. Thank you. Good question.
I think I said that before, but that's not correct. Yeah. Okay, so that's kind of cool, right? So I think this is fantastic. This is a great way to express an abstract encoder decoder. Then they define this little generator thing. So let's just take a look at this. Very simple linear plus softmax. So you give me some x, I'm going to project it using some linear thing and then some softmax thing. So a very, very simple little module. Okay, so now they get into the meat of it. So they're going to talk about the encoder stack and the decoder stack. So remember that the stack, what we mean by stack, is we mean that there's 6 of these things. And so they have a very simple little class called encoder that just takes a single layer of your encoder and then replicates it n times. Okay, so it calls this clones thing. And clones produces a deep copy of whatever layer you hand me. So you hand me a layer, I'm going to copy it n times. And then what I'm going to do in the forward pass is I'm going to iterate over each of those n things, and I'm going to take my initial x, whatever the input is, pass it to the first layer, then take its output, pass it as the input to the next layer, take that guy's output, pass it, etc. So all this is doing is nx. Like this class is implementing the replicate this 6 times bit of it. Again, you have to give me something called a layer. Oh yeah, and then there's this layer norm thing, which is like batch norm except a layer norm. We're going to worry about that. Okay, so you hand me a layer, and then I will use it to help build up an encoder. Layer norm just is a very particular kind of normalization. So you calculate the mean and standard deviation and normalize stuff. We talked about this briefly. I don't think it's important for what I want to accomplish here. Okay, so then we start looking. So let's look inside now one of these boxes. So they call these sublayers. So this little bit right here is a sublayer, and this little bit right here is a sublayer. So sorry. So let's look at some sublayers. So here is, and let's see if we can get this. So there's a sublayer connection, which is a residual connection. So you can see here, the forward pass of this is you give me an x, I take that x, and I add, and then I do dropout on whatever sublayer object you give me. So I'm going to take the x, pass it through a norm thing, pass it through the sublayer thing, do dropout, and then add it to x. So all that's doing is implementing the general idea of this line right here, add and norm, which you can see is used many, many times. So anytime there's a residual connection, we're actually doing add and norm. Yeah.
Is it normal to just do dropout like every time you have a skip connection?
Yeah, can be. So you can throw a dropout anywhere you want. So regularization is important. I mean, this model has a lot of parameters in it. Okay, so that's what this is doing. So this is just the general idea of a residual connection followed by a norm. And then here is the multi-headed attention mechanism. And the decoder then is very similar. You stack a bunch of decoders, layers. So you again see that clones thing, so it's replicating this, except we're gonna pass it a different kind of thing. Here's what a decoder layer looks like. There's some attention, some self-attention, some source attention, a little feed-forward thing, etc. Okay, sorry, any questions up to this point? Okay, the last thing that they show how to do is they mask this stuff with a positional mask. This is because on the decoding side, you don't want to cheat. And when you're decoding words, you can't look into the future of words that you haven't decoded yet. So, because I'm going to give you the target, when I translate one sentence to another sentence, and I want to output all of the things on this output side, I have all of the truth